Here I'm going to talk about heaps and how they can be used for sorting. The most common heap is a binary heap, which is implemented with a binary tree and follows two properties. The first is the structural property. Every row of the tree should be filled, except possibly the last. The last row should be filled from left to right. In this example, this tree breaks the property and is not a heap. While everything but the last row is filled, cards in the bottom row aren't as far left as they should be. The other property is the ordering property. Each item in the heap should be in order with its children. This video will be using min heaps, so the parents should be less than or equal to its children. In this example, the root is larger than its children, so it breaks the ordering property and is also not a heap. One method of creating a heap is by inserting keys one at a time. As we insert items, we fill it from the topmost unfilled row and add from left to right. In most cases, a card will eventually be added that breaks the ordering property. Because of this, we use the upheap algorithm, which will swap the new key up the tree along a path until it is no longer smaller than its parent, or has reached the root node. When adding the 8, we should perform upheap, which will swap it with the 9 and restore order to the heap. We must also swap the 2 up the tree, since it is smaller than its parent. Unlike the last one swap isn't enough, so we do it once more, making the 2 the new root for this tree. We can make a heap from 2 valid heaps and a new key by making the key the root and the heaps the subtrees, and then performing downheap on the new key. To perform downheap, we take the smaller of the node's children and swap it if it is also smaller than the node, and then repeat until the node is smaller than both of its children or has reached the bottom of the tree. By using this method, we can do an in-place heap creation. If you think about it, a tree with only one item is a heap since it meets both the structural and ordering property. This means that each leaf in this tree is its own heap. Starting from the bottom, we can take 2 heaps, which are the leaves, and a new key, which is the parent, and combine them to create a new heap. By performing this on all of the items in the bottom 2 rows, we create a few larger heaps. Using these larger heaps, we can move up a level and perform the process again, using the parents as the new key and the subtrees as the heaps. This right one happens to already be a heap and does not require any swapping. When we are left with 2 heaps in the root, we do it once more and have finished building our heap in place. When removing an item from the heap, we will remove the root node, which will be the smallest item in the heap. Now we must replace it in such a way that we don't violate our 2 properties. Bringing up the rightmost item from the bottom row prevents us from breaking the structural property. And then using downheap will restore the ordering property, giving us a valid heap once again. This process can be repeated until all of the items have been removed. Because we remove the smallest item each time, items are removed in order from least to greatest. This is how heapsort accomplishes its sorting. I discussed this in my video about trees, so feel free to refer to it if this doesn't make sense. A binary tree can be represented using an array. For every item located at index I, the left child will be located at 2i, and the right will be located at 2i plus 1, as long as the root starts at index 1. So here, 5 will be located at index 3, and its children will be located at indices 6 and 7. Using an array, we can perform an in-place sort using heapsort. Even though the cards are laid out like a tree, keep in mind that they are being stored in an array. I will give an abstract view of the array at the bottom. When an item is removed, it is held in a temporary variable. We move up the bottom rightmost item in our array and downheap as before. However, we will place the removed item in the empty spot. Even though the card is still in the array, we should not consider it part of our heap. I will turn the cards over to help demonstrate this. Using this method, we need a variable to keep track of the heap size, so we know which items in the array are part of the heap and which aren't. The heap will include all items from index 1 to the heap size. When our heap size reaches 0, all the items have been removed from the heap. Notice that the items in the array are now in order opposite to our ordering. Since this was a min heap, it goes from largest to smallest, so by reversing it, we have all of our items arranged from smallest to largest. Overall, heapsort has a runtime that is big O and log n, making it a pretty good choice for sorting.